Hello, this Recitation 9 video is going to cover the central limit theorems and for sample proportion and sample mean. Task 1. When a truckload of apples arrives at a packing plant, a random sample of 150 is selected and examined for bruises, discoloration, and other defects. The whole truckload will be rejected if more than 5% of the sample is unsatisfactory. Suppose that, in fact, 8% of the apples on the truck do not meet the desired standard. What's the probability that the shipment will be accepted anyway? Okay, so here I just wrote down the information we were given on the previous slide where we have a sample size of n equal to 150, and given that 8% of the apples are unsatisfactory, the probability of an apple being unsatisfactory is 0.08 or 8%. So here we need to first check two conditions. So the first condition is the 10% condition. So a random sample of 150 apples is taken from each truck, and 150 is less than 10% of all apples. So that condition is met. And then two, the success failure condition. So the success, which is the sample size times the probability of success, and then the failure condition, the sample size multiplied by the 1 minus the probability of success, which is the probability of failure. So here, n times p hat would be 150 times 0.08, which equals 12, and that's greater than 10. So that condition is met. Well, we still have to do the failure part. So n times 1 minus p is 150 times 1 minus 0.08, which is 0.92, which equals 138, which is also greater than 10. So because both of these lines are greater than 10, the success failure condition is met. Therefore, the sampling distribution model for our p hat follows a normal distribution, and we have our mean being p hat and our standard deviation being p hat, the square root of p hat times 1 minus p hat, which is our failure probability or proportion divided by n. And so our p hat is 0.08, our success probability. So, and our standard, so that's going to be our mean is 0.08, and our standard error is going to be 0.08 times 1 minus 0.08 divided by 150, and then you take the square root of that, which gives us 0.0222. So that gives us our sampling distribution. And then the probability of shipment will be accepted equals the probability that our p hat is less than 0.05. And so to find that, I like drawing our normal curve because we're in a normal distribution. And our mean, so it's centered around 0.08. And then our, we want to know the probability that our p hat is less than 0.05. So here's 0.05 would be somewhere on the number line here. And so we want to know that probability of being less than that. So that's the area under the curve to the left of 0.05. So here we would do normal CDF on our calculator from negative infinity, and in our calculator we would do negative 10 to the 10. And then so it goes from left to right. So our upper bound is going to be 0.05 here. And then next is the mean, which is 0.08, and then the standard deviation, which is 0.0222. Oh, so then, sorry, that gives us 0.08829. All right, so task 2. It's believed that 5% of children have a gene that may be linked to juvenile diabetes. Researchers, hoping to track 30 of these children for several years, test 742 newborns for the presence of this gene. A, the sampling distribution of the proportion of children with gene linked to juvenile diabetes is best described as, so we have to find that sampling distribution, And then B is, what is the probability that they find enough subjects for their study? So part A is to find that sampling distribution. So like task 2, we have the same conditions to check. So we have the 10% condition. So we will assume that 742 newborns are representative of all newborns, and these 742 newborns certainly represent less than 10% of all newborns. So, and then our second condition is the success failure condition. So n times p hat is 742 times 0.05. So that's going to be 37.1. And here we got 0.05 from, it's believed that 5% of children have this gene. So that's why our p hat is 5%. And that's the success. So it's a success if you have the gene. So that's greater than 10. And then n times the failure, that proportion. So n times 1 minus p hat, that equals 742 times 1 minus 0.05, which is 0.95, which gives us 704.9. That's greater than 10, so that condition is also met, so we're good there. Therefore, the sampling distribution model for p hat follows a normal distribution with mean p hat and the standard deviation of the square root of p hat times 1 minus p hat over n. And so here we set our p hats 5% or 0.05. So because all conditions are satisfied, the sampling distribution of p hat follows a normal distribution with mean 0.05 and then standard deviation of 0.05 times 1 minus 0.05 divided by 742, and then you take the square root of that, which equals 0.008001. And then part B, what is the probability that they find enough subjects for their study? So that's the probability that our p hat is greater than or equal to 30 over 742. So, and we got 30 from here. Researchers are hoping to track 30 of these children for several years. Okay, so if they find enough subjects, that means that we have over 30 or above. So here, if we set up our problem, we're going to draw a normal curve, and we have it's centered around the mean, which we determined in A that it's 0.05, and it was given to us. And then we were also, and then 30 divided by 742, that equals 0.0404313. So if I put that on the number line, it's going to be somewhere here. And so we want to find the probability or the area under the curve from that value to the right. We want it greater than that value. So we're going to do normal CDF, and this function goes from left to right. So our lower bound is 30 over 742, or this decimal here. And then our upper bound's infinity, or 10 to the 10. And then our mean is 0.05, and our standard deviation we found from above, which is 0.008001. So once you put that in your calculator, you'll get that this area under the curve is 0.884139. All right, task 3. Oops, sorry. Assume that the duration of human pregnancies can be described by a normal model with mean 266 days and standard deviation 16 days. And I copied the questions on the next page, so I'm just going to flip to that to save time. Okay, so what percentage of pregnancies should last between 270 and 280 days? So here's where I copied the information that we were given before, where we have assumed that the normal duration of human pregnancies can be described by a normal model, and our mean is 266 days, and our standard deviation is 16 days. Okay, so here we want to find the probability where our pregnancies last between 270 and 280. So we can set this up here, and to get practice with using z-scores, I found the z-scores for each. I first standardized these. So to standardize into z-scores, so the z-score of 270, so that's going to be x, which is 270, minus the mean, which is 266, divided by the standard deviation, which is 16. So that gives us 0.25. So that's our z-score for 270. And then our z-score for 280, we're going to do 280 minus the mean, which is 266 days, divided by 16, which is our standard deviation. We get 0.875. So that's our z-score here. So this, writing the probability of x in between 270 and 280 is equivalent to saying the probability of our standardized variable, so z, in between 0.25 and 0.875. And so here I drew my normal curve, and since I standardized it, it follows a normal distribution with mean 0 and standard deviation 1, so it's centered around 0. And so I also wrote on the number line where 0.25 would fall, which is the z-score for 270, and then 0.875, which is the z-score for 280. And so I want to find the probability of x being in between these two values. So I first need to find this area of this blue region here, and then also the area of the green region, which is all the way from negative infinity to 0.25. And I can take that difference, and then all that will be left is this region here. And so that's what I do. So I want to find first the probability of z being less than 0.875. So I'm going to do normal CDF, where I have negative infinity, so negative 10 to the 10, or in the previous video, recitation video, I did negative 9e to 99, but you'll get the same answer. So basically this represents negative infinity, and then the upper bound is 0.875, and then since I standardized it and I'm using these values, we have a mean 0 and standard deviation 1. You can solve this without standardizing it too. If you were to solve it without standardizing it, you would do negative 10 to the 10, and then this value here would be 280, and then you would have the mean being 266, and then the standard deviation being 16 days. Okay, so anyway, so you get 0.8092, that's the green region, so that's this whole region here, if you look at my cursor. And then we want to find this region here, this blue region, and then we'll take the difference. So the blue region is from negative infinity to 0.25, or if you don't standardize it, it would be negative infinity to 270. And then standardized, the mean is 0, standard deviation 1. If you don't standardize it, the mean is 266 and the standard deviation is 16. Either way, you should get for the blue region 0.59870. And so once you take that difference, you'll get 0.2105. That's the area under the curve here. And that's what we're interested in, is the probability that x falls between these two values, or z falls between these two values. That's this region here. So the area under the curve is 0.2105. Or you can think of it as a percent. So multiply it by 100, move that decimal place over 2, and then you get 21.1%. So it's asking for the percentage of pregnancy. So the final answer should be in a percentage. Okay, and then part B, at least how many days should the longest 25% of all pregnancies last? So here, if I were to draw my normal curve here, I didn't standardize it. So it's centered around 266, which is the mean that we were given. And so the question is how many, so the longest 25% is going to be this right tail here. Because here would be the shorter pregnancies, and then as you go to the right, you would get the longest pregnancies here. So we want to know what this question mark is, what this value is on the number line. So we'll use inverse norm, but because the inverse norm, goes from left to right, we have to use the area under the curve from the left to the right, which would be 1 minus 0.25 or 25%, which is 0.75. So here are what we enter in this inverse norm function is 0.75. And then we have the mean 266 and then standard deviation 16. So that gives us this value here, which is 276.792 days. All right, we're still in task 3. Now this is part C. Suppose that a certain obstetrician is currently providing prenatal care to 60 pregnant women. Let Y bar represent the mean length of their pregnancies. According to the central limit theorem, what is the distribution of this sample mean Y bar? Specify the model, mean, and standard deviation. Okay, so the distribution, this is similar to task 1 and task 2, but by central limit theorem, the sampling distribution for sample mean length of their pregnancies is approximately normal distributed, where we have the mean is going to be the same as the sampled population, so that's going to be 266 days. And then the standard deviation will be the standard deviation divided by the square root of n. So that's going to be 16 divided by the square root of 60, which is 2.06559 or 2.07 days. So to rewrite it, we have our Y bar. The distribution of Y bar follows a normal distribution with mean 266 days and standard deviation 2.07 days. And then part D, what is the probability that the mean duration of these patients' pregnancies will be less than 260 days? So here we would want to find the probability that Y is less than 260. So here I'm going to draw my normal curve. Our mean is 266, but our standard deviation is 2.07. That's what we found in C. And so we want to find the area under the curve from -infinity to 260. So our lower bound is going to be -9 E99, or you could do -10 to the 10. And then our upper bound is 260. And then our mean for the Y bar distribution is 266, and the standard deviation is 2.07. So that gives us 0.001875 or 0.002 if you round, and that's that area under the curve. That's the probability that we were looking for. All right, task 4. So task 4, the weight of potato chips in a medium-sized bag is stated to be 10 ounces. The amount that the packaging machine puts in these bags is believed to have a normal model with mean 10.2 ounces and standard deviation 0.12 ounces. What fraction of all bags sold are underweight? Okay, so here we want to find, again, we were told that the weight of potato chips in a medium-sized bag is stated to be 10 ounces. So if it's underweight, then it would be less than 10 ounces. So we want to find the probability that X is less than 10. So here I'm going to draw my our normal distribution centered around 10.2. That's our mean. And here 10 on the number line is going to fall somewhere to the left of 10.2. So I want to find this shaded area here to find the probability that X is less than 10. So we're going to do our normal CDF function from -infinity 2 or negative 10 to the 10 to 10, and then our mean is 10.2 and our standard deviation is 0.12. So that gives us 0.0478. That's that area under the curve. So that's the fraction of all bags sold that are underweight. All right, next is some of the chips are sold in bargain packs of 3 bags. What is the probability that none of the 3 is underweight? So if they're not underweight, that means that they would be greater than 10. So we want to find this for 3 bags, but first, what we'll do is we'll find it for 1 bag, and then we can multiply this, or we can cube this or multiply this by itself, but 3 times for 3 bags. So first, let's just figure it out for 1 bag. So the probability that x is greater than 10 is going to be, well, we already found this area here under the curve to the left of 10. So this remaining area under the curve, we can do 1 minus 0.0478, which is what we found in part A, which is 0.9522. So that gives us the area under the curve to the right of 10, or in other words, the probability that x is greater than 10. So now that we have that value, and that's for 1 single bag, we can cube that for 3 bags since each bag is independently packaged. And so when you do 0.9522 cubed, you get 0.8633. That is the answer that we're looking for. So that's the probability that none of the 3 bags is underweight. All right, and then part C, which is the last part of this task. So what is the probability that the mean weight of 3 bags is below the stated amount? So the mean of the sample mean weight distribution will be the same as the population mean. So that's going to be 10.2. And then like task 3, the standard deviation of the sample mean weight distribution is going to be our standard deviation divided by the square root of our sample size n. So that's going to be 0.12 we were given as the standard deviation, and our sample size here is going to be 3, n equal to 3, because here we're given 3 bags. So that's our sample size. So we're going to do 0.12 divided by the square root of 3, and that gives us 0.06928. So now we have that distribution where the mean is 10.2 and the standard deviation is 0.06928. And so now we want to find the probability that the mean weight of these 3 bags is below the stated amount. So that would be below 10. So that's going to be the probability that, x is going to be less than 10. So we have, we're going to do the normal CDF function. So similar to before, negative infinity or negative 10 to the 10 to 10. And then our mean is going to be the same, 10.2, but instead, now we're going to have this as our standard deviation, which is for the mean weight of 3 bags. So that's 0.06928. So this value is different than when we solved it in point A, because this is what we were given in point A, but now we're working with the mean weight of the 3 bags, x bar. Okay, so once you solve that in your calculator, you get 0.0019, and that is the area under the curve here, and that's what we're looking for. That's the probability that the mean weight of the 3 bags is below the stated amount. And this concludes recitation. I hope this was helpful.